a video to help everyone from hobbyists to labs test pH better. You don't need to be a chemist, but you do need to know a bit about pH. In technical terms, pH, or potential of hydrogen, is the hydrogen ion activity in a solution. It's measured on a logarithmic scale of 0 to 14, with 7 being neutral because the activity of positively charged hydrogen ions and negatively charged hydroxide ions is equal. At low pH values, from 1 to 6, the hydrogen ion activity is greater, so the solution is considered acidic. At high pH values, from 8 to 14, the hydroxide ion activity is greater and the solution is considered basic. There are 3 important things to know. 1, you are measuring tiny concentrations, which is why pH meters are delicate. Maintenance is key to accurate pH measurement, but there will be more on that later. 2, pH readings are affected by temperature, so you need to account for that. For example, a pH of 7 at 25 degrees Celsius may read differently at 20 degrees Celsius. 3, pH is a logarithmic scale. This means that a reading of 7 pH has a 10 times higher concentration of hydrogen ions compared with a reading of 6 pH. Small differences in readings can matter a lot. A pH measuring system consists of 4 main parts: a pH sensing half cell, a reference electrode half cell, a special meter to display your pH value, and your sample solution. Together, these form an electrochemical circuit that measures and displays the pH of your sample. Every pH meter has an electrode or probe. Until the 1970s, it was common practice to offer 2 half cells separately, a glass pH sensor and a reference electrode cell. Today, it's more common to use a single combined electrode that has both sensing and reference components. The combination pH electrode has a layer that's sensitive to hydrogen ion activity. Inside the electrode, there's a reference cell. The electrode creates a current that measures the charge on the glass tip compared to the reference solution. Keeping this bulb in good condition is vital. As a result of immersions in samples, a residue can form that stops the ions from binding or slows the process down. The binding layer can also get damaged. It cannot be repaired if it's damaged. Remember also that the electrode is a consumable. The binding layer will get less sensitive over time, and the electrode eventually will need to be replaced. This is true for all pH electrodes. The next part of the pH measuring system is the meter itself. The meter processes the voltage from the electrochemical cell and converts it to a meaningful measurement unit, pH. The final part of the measuring system, your sample, is the connection between the sensing electrode and the reference electrode. This connection allows the entire measuring circuit to work. pH electrodes come in a variety of designs, but they all have some key parts. When choosing a pH electrode, design considerations include the type and shape of the glass, junction material, and body material. First, the glass membrane. Hanna Instruments produces 4 different glass types covering a vast number of pH applications. General purpose glass provides the greatest response over the entire pH range and can be used for a wide variety of applications. Low temperature glass membranes have a lower impedance and are suitable for samples at lower temperatures and lower conductivities. Designed for extended use at elevated temperatures where glass impedance is known to decrease, high temperature glass offers a higher resistance, making it possible to obtain accurate results with excellent response times. HF-resistant glass is made for aggressive applications containing fluoride ions, which dissolves glass. This glass composition will ensure a much longer life for your pH electrode. Here's a sensing bulb on a simple tester, and here's what it looks like on a laboratory-grade electrode. The pH sensing bulb can come in a variety of shapes. Each shape serves a unique purpose. Spheric tips are recommended for general use in aqueous solutions. The round bulb geometry is the most common shape for a glass pH membrane and provides a wide surface area for a variety of liquid samples to contact. Conic designs are ideal for direct penetration into samples due to their pointed profile and geometric strength meter with your application-specific electrode. If you have a refillable electrode, make sure that the electrolyte fill level is at least ½ an inch from the fill hole or closer. Check the electrolyte for contamination and refill it with more electrolyte if necessary. You'll also need buffer solutions. Standard calibration buffers are 4.01 pH, 7.01 pH, and 10.01 pH. Depending on your sample, you may need different buffers. When calibrating a pH electrode, it's important to choose buffers that bracket the expected reading. For example, if the expected reading is pH 5.2, then it would be best to calibrate to pH 4.01 and pH 7.01. If the expected reading is pH 3.4 after using a cleaning solution. We recommend calibrating daily for best results. However, if high accuracy is not crucial to your measurements, it's okay to calibrate once or twice a week. Here's an example of a 2-point calibration using a basic pH tester. For this tester, we will stir manually. The things you'll need for this calibration are clean beakers for your pH 4.01 and 7.01 buffers, a beaker for your rinse waste, a DI water rinse bottle, and of course, your pH tester. The first thing you want to do is rinse your electrode with your DI water. Enter the calibration mode on your tester